everybody. Welcome to the lesson on the two-way analysis of variance. Before we get into that, let's do a little bit of review about the one-way analysis of variance, or just the plain old ANOVA. If they leave off the one way, it's implied, which was the test to compare more than two means. And we could think about it as our numeric variable being the dependent variable, and our categorical variable being the independent variable. So our grouping variable might also be called the factor, and we're comparing across levels of the factor. The example we did was whether there's a difference in the amount of time a child spends watching TV per week based on their family structure, whether they live with both parents, a parent and a step-parent, or a single parent. And we wanted to know, was that factor significant in predicting the amount of TV the child watches per week? So with two-way ANOVA, we're doing all of that, plus we're adding a second categorical variable as our independent variable. So I put some examples here. We could look at the same thing we looked at before, but also look at the same time in the same analysis, the child's gender, to see whether there's a difference between the amount of TV that boys and girls spend watching each other. I've got another example here. Does the mean amount of time to germinate a seed differ based on these two variables? One variable would be whether it's in fertilized soil, yes or no, and whether it's in a greenhouse, yes or no. So that would be two variables, each of which would have two levels. In this first one up here, family structure was a variable and it had three levels, and gender is a variable, and in that data set we had, it had two levels. We want to be inclusive, so want to be aware that that gender is not binary always, but in that data set it was. Third one has two independent variables, two factors. The time students take a math class, and there were three levels, so 8 a.m., noon, or 3 p.m., and then whether the student is a student athlete. And that would be two levels, yes or no. So every two-way ANOVA has three sets of hypotheses that we're testing. So we're not going to list these anymore as, H naught, mu1 equals mu2, whatever anymore. We're just going to list that these are the three things where these basically are our three alternative hypotheses. The first one is that the means differ based on the first factor. So if we're looking at this example up here, the one we looked at before, family structure. Is there a difference based on family structure? The second hypothesis is there a difference by the second variable, gender? And then third, is there an interaction between the variables? So what do we mean by interaction? Well, sometimes it's possible that the dependent variable behaves differently for a combination of variables than it does for just one variable at a time. I made up this third example to show what an interaction might look like. So in my experience, teaching classes, I know students hate 8 a.m. classes. And, you know, they're groggy and cranky, and because of that, they're just not their best and don't do as well. That's most students. So most students, I think, would do better at noon, followed by 3 p.m., followed by 8 a.m. Okay, that's just my prediction. The exception would be student athletes. They already have to be up for, I don't know, 4 a.m. sprints or whatever they have to do. Total respect for that, by the way. Couldn't get up at 4 a.m. for anything. But because they're up already and having to, you know, do whatever they have to do early, 8 a.m. is nothing to them. So they're perfectly comfortable. So they are not at their worst at 8 a.m., at least in my experience. And this is, you know, broad strokes, and there are exceptions and whatever. But yeah. So my guess would be that student athletes would have a different pattern of what times of day are their peaks. And you guys probably know better than I do what that might be. But if you suppose that most students would do best at noon, followed by 3 p.m., followed by 8 a.m., but then imagine that maybe student athletes are kind of the other way around. They're best at 8 a.m., followed by noon, and then by 3 p.m. they're tired out. That's what an interaction looks like. So the interaction is if there, well, I'll just say if there's an interaction between the variables. Let me show you what I mean graphically. So we're going to look at these things called profile plots. And this is one that we're going to see in just a minute for an example we're going to be working with. I'll go ahead and tell you about this example. This example is on chest deceleration. So we've got data on different kinds of cars and how they perform in basically crash tests. Chest deceleration is a measure of how much, basically how much force is exerted on your chest when you stop all of a sudden. So lower chest deceleration means that you've got less impact, essentially, on your chest. That's probably not a great way to explain that in terms of the physics, but basically lower chest deceleration means less damage to the person in a crash. So, in a profile plot, we've got our dependent variable is on the y-axis. Okay, so here on the y-axis we've got chest deceleration, and this I believe is in meters per second squared. We've got one of our factors on the x-axis. So one of our factors has 3 levels, the size, small, mid-size, and large. And then our other factor is represented by separate lines. So we've got whether the car is foreign or domestic. And foreign cars are in this blue line up here, and domestic cars are in this red line down here. You need to be able to read these plots. They're very, very useful and very informative if you know how to read them. So basically, when you look at these plots, factor 1, the one that's on the x-axis, has a main effect if the lines are not horizontal. Okay, so in this case, we've got, our lines are not horizontal, which means that we've got less deceleration in the large cars than in the small cars. Which I guess makes sense, that the small cars would stop a lot harder than the large ones, which might absorb a lot of the pressure there. So it looks like, based on this, that we're probably going to have a main effect of the first factor. There's a main effect of the second factor if these lines are of different heights. So these lines look like consistently it looks like consistently foreign cars have higher chest deceleration than domestic cars. So based on this, it looks like there is going to be a main effect of whether the car is foreign or domestic. There's an interaction if the lines are not parallel. So if the lines are, in this case, these lines look like they're pretty much parallel to me. Now all of this, I should say, all of this is subjective. We're going to look at the significance tests here in a minute, but you know, for right now, those don't look terribly non-parallel to me. But that's my opinion of it. What this tells us is that for both foreign and domestic cars, small cars have the highest chest deceleration, followed by the mid-sized cars, followed by the large cars. And that's true for all of them, which means that the foreign cars aren't behaving differently on that from the domestic cars. I've got this, which I just flat out stole from the Six Sigma website. Theirs is temperature versus pressure. So this is the temperature and this is the pressure. And this is showing all of the different combinations of main effect of this variable versus main effect of this variable versus the interaction. Here there's a main effect of pressure, but not temperature. And that's because this line is not horizontal, which means that temperature is higher at the second temperature than at the first temperature. But these lines are not different from each other, so pressure has no bearing on it at all. So pressure has no effect. And I won't explain all of these, but I will show you just a couple more of these. This one, you have an interaction, and that's because, you know, these are not parallel. But there's not a main effect of either one of them. The reason is that if you sort of average these two together, you know, met in the middle, you'd get a horizontal line, which means temperature is not a factor. It's not there's no effect of temperature. And if you kind of average these together, these lines would be on top of each other, meaning that neither one of these is higher than the other one. Okay, so I'll let you take some time to study these. These first four have no interaction, but they do have main effects, different combinations of main effects. And then these last four do have interactions with different kinds of main effects. So I'll let you study those. So if we want to run our hypothesis test, so we're looking over here at our data set, and to run our two-way ANOVA, we're going to analyze general linear model, and I'll point out that there's a generalized linear models as well, but that's not what we want. We want general linear model, and we'll pick univariate. Univariate means that there's just one dependent variable. It is possible to run an ANOVA with more than one dependent variable. It's called MANOVA, multivariate analysis of variance. Anyway, so we want to take our dependent variable, the numeric one, and put it here under dependent variable. And we're always going to put these under fixed factors. Okay, there's not really much of a difference. Just always put those under fixed factors. Now, under options, let's click descriptive statistics. And to help us out later, let's click effect size, estimates of effect size. And we'll click continue. And to see this plot that we're talking about, click plots. And you want to put one variable on the horizontal axis and the other one as separate lines. The plot reads better if you've got one of the variables that's got more levels than the other one. Put the one with the most levels on the horizontal axis. So size has 3 levels, but the 4DOM variable only has 2. So we'll put size on the horizontal axis. And then you got to hit add. Click continue. And then click OK. And this gives us our output, including this profile plot that we were looking at a minute ago. And I've got all the instructions listed in here. So, some stuff for us to look at. First of all, here, this tells us, I've copied all this output over here. So, this is the same thing as over there. This tells us our sample sizes. So this tells us that we've got 6 observations in each combination. No, that's not true. It tells us we've got 6 small, 6 mid-size, and 6 large, and then we've got 9 foreign and 9 domestic. Down here you can see that we only have 3 in each combination. So we have 3 small foreign cars, 3 small domestic cars, etc. So that's just our sample sizes. That's not all that useful. Descriptive statistics can be very informative. We get to see each combination, but you also get to see the totals. So you can see that for small cars, let's see, for small cars, their total mean was 45. And you can see the standard deviation there. You can also see for mid-size was 41.8. And then for large, it is 37.8. So you can see the same thing we saw on that graph, which is that the larger the car, the less the chest deceleration. You can also see the totals for foreign and domestic. Foreign cars have a mean of 44.1 meters per second squared of chest deceleration, and then the domestic is 39.0. So that's your descriptives. All right, so our ANOVA table has gotten substantially more complicated. But there's really just a few things on here we need. So size is our factor 1. 4dom is our factor 2. Write that a little bit better. And this one is our interaction. Okay, so where there's the star there, that means that's the interaction between size and foreign or domestic. And we're still looking at our column for the F values and our column for the P values. This is where our P values are. So let's start by looking at our first main effect. So we don't care about the corrected model or the intercept. Let's look at the size, which I'm circling in blue. So for size, it has an F value of 3.581 and a P value of 0.06. This tells us that there is not a significant effect of size. This P value is too large. So no main effect. Of size. Let's look next at the foreign or domestic. Circle that one in red. FORDOM has an F statistic of 5.440 and a p-value of 0.038. So there is a main effect. Of this variable. Okay, so it looks like that there is a difference between the chest deceleration for foreign cars as domestic. And then let's look at the interaction. So the interaction has an F value of 0.342 and a P of 0.717. So there's no interaction. So there's no significant interaction here. All right. So that's all we need from there for now. We'll come back and look at these partial eta squares in a minute. Before we actually do that, though, and I did all this with you because I wanted you to, before I started talking about assumptions, I thought we should talk about what the test was. But we should talk about what the assumptions are. So there are two key assumptions of the two-way ANOVA. One is that each sample, and by that I mean each combination of factors, follows approximately a normal distribution. So I'm talking about the three values in, well, let me go back up here and show you what I'm talking about. So the three in the small foreign cars follow a normal distribution. The three in the small domestic cars follow a normal distribution. The three in the mid-foreign, etc. Obviously, with a sample size of just 3, we're not going to be able to tell whether this follows a normal distribution. That's a reality of collecting data. You imagine a lot of the data that you collect, something like this, if each one of these observations represents, a car crash, a crash test that they've had to do, each one of those is going to be very expensive to get. So you can't get huge sample sizes for each group. So that's just something we have to, live with. Anyway, so I would say that, at this point in the course, you have done you've gotten a ton of practice in evaluating normality. So, for the rest of the course, unless I specify otherwise, you are exempt from evaluating normality. You can just assume it wherever you need it. Okay? I think you've proven that you can do that. The other main assumption is that there's a constant variance across all of those different combinations. So here we've got 2 levels of one factor and 3 levels of another, so 6 combinations, that all of those have a constant variance. The term for constant variance is homoscedasticity. Sometimes this is spelled with a K and sometimes with a C, but that's a fun word to bring out at parties, make people's eyes glaze over. As you talk about normal probability plots and homoscedasticity, and sorry, I'm being silly. Anyway, good news, bad news here. The way you should check for that, and don't do this, just watch for now. Well, forever. The way you should test for that is under options, homogeneity tests. However, for some reason, this version of SPSS has a bug with that test, and it will shut down SPSS. So if you're welcome to try it and test it, and see if it does. But I've looked it up online. I'm not the only one who's found this. There's a bug. So you get a free pass on that because I am talking about Excel. SPSS returns an error. So you are exempt from evaluating this assumption. Okay? So next time they come out with a new version, hopefully they'll get that fixed. All right, so assumptions. You got it easy on assumptions here. Now, let's talk about effect size. The effect size is something called partial eta squared. Eta is a Greek letter that looks like I think it's supposed to be an H. I think that's what our equivalent is. That's terrible. But it's partial eta squared, which is similar to r squared. In fact, for one-way ANOVA, they are the same thing. Here's what you need to know about this. Partial eta squared is a less than ideal measure of effect size. It's an attempt to figure out, of your two variables and your interaction, how much of the variability in your dependent variable can be explained by each one of these. The first factor, the second factor, and the interaction. But since that's not technically correct, I mean, it's an attempt to parse out how much of the variance is accounted for by each one of those. But it's not correct to say these percentages are the variance accounted for. So don't use that interpretation. In general, researchers will say that 0.01 as a partial eta squared is small, 0.09 is moderate, and 0.25 is large. But keep in mind that you're not really comparing those objectively to these measures. You're comparing them to other models and other variables. Basically, what you need to know is to state your partial eta squared. So for each one of these, when you state your results, you're going to state the partial eta squared. And I've got, I want to mention it in terms of the symbols. I want you to use the correct symbol. So I've got, and I'll post this. I've got these symbols here, and I'll put them there where you can just copy and paste them. Because I want you to, don't just put h squared or something. Okay, so I want to see that precisely. All right, post hoc tests. Post hoc tests are not needed for variables that are not significant or variables that have just two categories. Because remember, the whole point of post hoc tests is to say, oh, there's a significant difference in this variable that's got 3 or more groups. Let me compare pairwise of those. And we're still going to run the Tukey tests. To get to the Tukey tests, going back to our general linear model univariate, and then look for post hoc, and then we wouldn't do a post hoc test for the foreign or domestic because it only has two values. But say size had come out to be statistically significant. It's got three or more levels, so we'll run our post hoc for that. So we'll take that, move it over. We'll pick Tukey, and we'll click Continue, and we'll click OK. And it's going to give us something very similar to what we had before. There it is. These multiple comparisons, which I've got over here. So according to this, the p-value for comparing small to mid-sized cars is 0.487. Small to large is 0.05. So some people would say reject H0, and some people would say fail to reject H0. I think you could reject H0 there. We generally reject H0 if p-value is less than 0.05, but some people say less than or equal to 0.05. So I think you could go ahead and reject H0 here, and say that there is a significant difference between small and large cars, but none of the other combinations have statistically significant differences. This is just if this had come out to be significant, though. This is just so I can show you what you would do. So for the write-up, we're going to do exactly what we did before. Start with a brief summary, talk about your assumptions, although we know that in this case, we don't have to evaluate those because, yay, Excel was broken. Make sure you state any relevant descriptive statistics. I would not state all of these. You can copy and paste this table and point to a couple of them that are important. In my write-up, I stated the means and standard deviations for foreign and domestic because that one was statistically significant. But I did not state them for the size of the car because it was not. But you have a lot of leeway on that. I will give you leeway as long as you do something that makes sense. Report the results of your hypothesis test. Always go ahead and report your partial eta squared here, even if it's not statistically significant. It doesn't hurt to go ahead and report that. And then for ones that are statistically significant, report the results of your post hoc tests. So I didn't have, in this one that we just did, we didn't need to run any post hoc tests, so I didn't talk about those here. But let's talk about this analysis a little bit. The first sentence is just our basic summary saying here's what we did. The second sentence, I said there's a significant effect of where the car was manufactured. And then, boy, it should be 0.038, not 0.380. So you state your F, your p-value, and your partial eta squared. And you can state that as partial eta squared or eta squared with a subscript of p, either one. And then even within that same sentence, I said foreign cars have a mean chest deceleration that's higher than foreign cars compared to domestic cars. And then I stated that neither the size of the car nor the interaction were significant. And then I didn't have any post hoc tests that I needed to report here. All right, so that's it for this lesson. I haven't decided yet, I may record a second video with a second example. So stay tuned for that. See you soon.